Okay. Hello, my name is Aiden Grossman. I'm currently an undergraduate student at UC Davis, and today I'm going to be talking about using machine learning for cost modeling and applying big data to that. So Viraj covered a decent amount of this, but benchmarking for everything. It's expensive, noisy. It's pretty expensive to do, can require restricted hardware features like performance counters. Deterministic performance results and fast performance results can make training machine learning models easier to replace compiler heuristics. It's also a lot easier to create these sort of learned cost models, assuming you have appropriate benchmarking infrastructure, as opposed to analytical cost models, which typically require a significant amount of reverse engineering effort, if you can even really do it feasibly due to lack of introspection into the hardware, like with the Zen architectures, which is really, there was a paper a couple weeks ago that opened some stuff up that wasn't really possible before. So for the data, essentially, when you want to train a learned cost model to take in snippets of code and spit out some performance numbers, in this case, it's going to be the inverse throughput of a basic block. You need a data set to be able to do that. So since we're at the basic block granularity, we construct a data set of a lot of basic blocks, in this case, about 1.5 billion. We use the basic block address map tooling to extract individual basic blocks. Previous attempts at this have used runtime instrumentation using Dynamorio, which can significantly limit the number of blocks that you're able to extract because you need to be able to actually run it, which takes quite a bit of effort. We post-process the extracted blocks to remove a couple of instructions like call, return, anything that works with the control flow, and also syscall instructions. And then for initial results, just experimenting right now to actually get some preliminary results, we code out all of the instructions that may load or store. It's just right now leaving to future work. All the infrastructure's there. I just need to actually write one patch and actually train the models on it. So for the dataset construction, we use compile, which is a large collection of about, the open split's about 600 gigabytes of bitcode across a couple 100,000 bitcode modules. So we take bitcode, we run it through a bunch of different pipelines. So we run it through the different opt pipelines and the different LLC pipelines. And then we get out a bunch of different basic blocks that we can then extract. Then we run the post-processing. And we get out there's a deduplication step because you end up with a lot of duplicated basic blocks, only about 30 to 40% kind of surprisingly. And then, we get out the data set at the end. And then once you have a bunch of basic blocks, we need to be able to benchmark them so we can have ground truth data. So to collect inverse throughput values, we use llvm-exegesis. It's a machine benchmarking tool that's upstream in LLVM. And then we use some custom Python scripts to parallelize the collection. So the results aren't extremely deterministic at this point. They're pretty close depending upon the system setup, like whether or not you have hyperthreading enabled and how many benchmarks you're running at the same time. And it's reasonable that we'd be able to push those numbers down quite a bit because right now we're using the Linux perf subsystem. So we use like a IOCTL syscall to turn the performance counters on and off. And there's going to be some variability there. And we could adjust it to use like the read performance management counter instructions, which are going to be constant latency, but the numbers are reasonable enough at this point. So on a couple different configurations, depending upon whether or not hyperthreading is enabled or disabled and how many benchmarks we're running at the same time, we can see run-to-run variabilities from about like 0.1% to 5%. The important thing to note here is depends upon like the accuracy that you actually need in like the run-to-run variance and the overall accuracy is dependent upon what the bottleneck ends up being. So right now the bottleneck ends up being how well the models are able to learn how to map the code into the performance data. So if your model is going to have an accuracy of about 10%, a run-to-run variability of 1% is perfectly fine. Ideally you want it to be as low as possible, but practically it might not make a difference. So in this case, just for the initial experiments, we used a large HPC system to collect a lot of data reasonably quickly. So we used we couldn't disable hyperthreading on the system, so we ran about 1 benchmark per core. So the run-to-run variability was about 1%. But it's just trade-offs there, because otherwise, I mean, we ended up using 90 nodes for about 2 hours on 96 thread systems. So it was a reasonable amount of compute to collect all the data. And then so for dealing with memory accesses, when you have basic blocks that access memory, you need to be able to set up the virtual address space to be able to actually execute them without hitting a seg fault, because the performance numbers make no sense when you hit a seg fault. So right now we just use an iterative technique. We run the basic block, see where it seg faults, map an address in there, and then do that over and over again until we either successfully execute the basic block or we hit some defined threshold. And we use the memory annotations feature in llvm-exegesis, which has support for doing all of this. So essentially it sort of looks like this. You take a basic block, you run it, and then you see that it seg faults at the address like at 8192. You set up your memory definition, you set up your memory mapping, and then it's able to successfully execute that basic block and get you a reasonable inverse throughput number. Yeah, one thing I do want to cover here are some of the assumptions that we're making with these models. So like with this model specifically, we're not looking at a lot of execution effects like cache misses and branch miss predictions. We're assuming everything hits L1 data cache. There's no TLB misses. The front end working properly. Pretty much ideal execution conditions, at least for these preliminary models. So yeah, there's a couple we make sure that all the memory definitions end up being in one page, so that on x86 with physically tagged memory, everything's easily able to fit in the L1 data cache. Yeah, there's a couple other nuances with NUMA nodes and making sure everything's set up properly there. And then, so with all that, I guess this probably should have been earlier, but so the raw deduplicated data set ends up being about 1.5 billion basic blocks. Post-processing, removing instructions, the instructions I mentioned earlier, we end up with about 1 billion basic blocks. And then post-processing to remove memory accessing instructions for the preliminary experiments, we end up with about 150 million basic blocks, which is still like about two orders of magnitude more than previous data sets. So the biggest previous open data set is about 300,000 basic blocks. And the previous biggest closed one that couldn't be opened because it has spec in it was about 1.4 to 1.5 million basic blocks. So even without even significantly limiting the data set size for simplicity in initial experiments, it's still significantly bigger. So for the cost model, the actual neural network that does the predictions, we're using the Granite architecture. So it's a graph neural network. You set up a graph containing a representation of the basic block. You get some embeddings out of that, and then you run it through a decoder, and then it's able to spit out a number that is hopefully representative of the inverse throughput of your basic block. So we do a couple different hyperparameter adjustments to the original model. And yeah, mostly going off the hypothesis that bigger data sets will end up increasing performance, which was demonstrated in the original paper, but not to the scale that we're doing here. So for initial results, using a little bit of a subset of the data set, we're getting mean absolute percent errors, like quite a bit less than what was demonstrated previously. These models only on 10 million basic blocks. As there wasn't, just moving on to future results, and that'll just be down the line. So yeah, the previous, so there aren't any numbers exactly for Zen version 2. So, and since the data set is a bit of a, it's a bit truncated and processed from other things. So we expect the results to generalize pretty well to previously architectures that have been worked on previously. But yeah, there's a couple nuances in the results here, but yeah, so we get a mean absolute percent error on a 10 million basic block data set of about 4.7% on an evaluation, on a validation subset that's separate, which is quite a bit better. It's about 2%, 2 percentages lower than like previous work where the average accuracy has been 6 to 8%. And given these results are only obtained on a significant, like a very small subset of the overall data that we have, and we would expect this trend to continue. Like not necessarily linearly, it's probably going to end up being an exponential decay on how much data you end up feeding it versus the performance that you get. But we have 2 orders of magnitude more data, so I would expect to be able to push the performance results by quite a bit. Yeah, so in terms of future stuff that I would have liked to have done, but haven't done yet. So training on the full data set, and then also, so more, and then, of course, doing memory accessing instructions. The infrastructure is pretty much all there. All the annotations and benchmarking infrastructure is there. It's just validating it and then making sure that CPU affinities are set properly to ensure that things are executing on the appropriate NUMA nodes so that you don't get weird results and run-to-run variabilities that are really high. And then additional hyperparameter tuning, because as we have more data, we're able to actually, we might end up saturating like what the neural network is able to learn, but we can just scale it up in terms of like the number of parameters, which should lead to better performance. And so since we have more data, we'd actually be able to train bigger models to compute optimality. And then in terms of future directions, we're looking at fine-tuning these models for execution information, like cache misses, like Viraj talked about earlier. Beyond basic block level cost modeling, so moving to things like whole functions. It's complicated by the availability of data because basic blocks, you can sort of fudge your way through executing them with, like fudging the register values and the memory accesses. But as you get to more complex code, that becomes more difficult to do. But potentially taking advantage of input generation or input capture, we should be able to do that. And it would, be able to bring these sorts of models, that make them significantly more useful. We're looking at also mutation-based fuzzing. So one of the problems with these models currently is that they're statistical machine learning. It learns the patterns in the data. And if the patterns in the data don't match what you're trying to evaluate it on, it doesn't work particularly well. So some previous work where they were doing a systematic investigations between different models, they looked at the learned cost models and they would do things like you'd permutate a register that the compiler didn't really do normally, and then suddenly your results would just be nonsense. So we're looking into doing things like mutation-based fuzzing, to work on making to add more data into the data set to make the models more invariant against that. Advantages over previous approaches. The tooling is productionized. It's all upstream LLVM and a couple pieces outside of it. And the model performance, at least so far, is better, and I would expect that trend to continue as we actually get full models finished training. And quite a few people helped with this project, and sponsored partially by Lawrence Livermore. And Q&A.
Cool. Questions?
So one of the questions is about the way that you generate the data set, because it feels like you're pretty closely coupled to the compiler that generates it. And if the compiler doesn't support some features of the computer you're targeting, you might just not cover a whole range of possible programs.
So that's definitely like something we've been in discussions about. Because, so right now, like we're not like AVX 512 instructions, we're just not generating those. But like the thing is, like really what like is here is like tooling. So it would just be kind of trivial to add the flag. Like you just go to it would be pretty trivial to add the flag in to tell LLVM to vectorize everything and just spit out that code. And then you create your own data set, you run the benchmarks, and then you just get out a model. And ideally, theoretically, you should be able to put everything into like a couple line shell script. You run it on a machine for a while and it spits out a model that supports those instructions.
Cool.
Wonderful. Thanks for the presentation. How long did it take for you to arrive at this point, enough to be able to give the talk, A, like number of months or how much effort you had to put in? And B, how did you choose the code that you chose to generate the bit code from?
Yeah, so this has been sort of an off and on project for a while. I started working on it maybe a little bit over a year ago, but like it's mostly been part-time work in between school and whatnot. There've only been like a couple weeks where I've really been able to put a lot of time into it. Yeah, and then so for the bit code, so we're just using the compiled data set. So the idea there is we want to try and pull from package ecosystems that are used in the real world theoretically. So we're using things like Rust crates, there's SPAC and HPC package manager, a couple other package ecosystems that theoretically, like there's a barrier to entry where someone has to actually put their code there. So it's hopefully representative of code that's used in the real world. And then, yeah, we're just pulling all the data from that. And then, so yeah, it probably skews a little bit because we have to conform to license constraints when we release it. Like we end up with a lot less C and C++ because a lot of C and C++ projects have complicated licensing. But yeah, that's at least the theory behind the dataset collection.
Any more?
I'm curious why you use, in your preparation, you use opt and LLC. Because technically they do the same thing, so you're just running opt twice. What is the...
well, so the idea is that we want to run, like, we're just trying to get different permutations of things. So LLC only runs the back end. So opt will run the middle end transformations, and then we're using LC to get the back end.
Ah, okay, you're right. Yep, sorry. Silly question.
Thanks for the talk. So you said that depending even like which register is allocated, you can give very awkward results.
Mm-hmm.
Can you teach it to understand that a register is a register, so you will pattern match through the thing that's looking at and understand it?
Yeah, so yeah, it's statistical machine learning. You can't really teach it to understand anything more than just like somehow these numbers multiplied together produce the right result. So it depends upon the ISA. So sometimes you can say like just this instruction with this register, but really you need to be able, so you have to model the dependencies correctly between the registers. So for that, and then also instruction encodings and whatnot can vary sometimes depending upon the ISA on the specific register that's used. So the way the graph is set up is essentially you have like an instruction mnemonic, and then you'll have like the registers that are used. So it can matter quite a bit, like depending, like in the instruction mnemonic, the actual encoding and thus the performance can vary quite a bit depending upon the exact registers that you use.
Okay, so because of the last two questions here, so there's different features that you might want to add to your data set, like you said AVX512 intrinsics, or you have a different ISA that you target altogether. And I mean, arguably, we don't want to redo everything. You don't want to start from scratch. Why would we? I mean, most of this is probably shared across all of them. I mean, their ISAs are not completely different. And also, that kind of brings me to the point, like, should we like build the base model and then go from there, provide that to the people? And if so, which is probably, the answer is probably true, is do we really want to start, like, do we really want to do this on ISA? So go one or two steps higher up the chain where we do ISA and LLVM-IR, only LLVM-IR, machine instructions, I don't know, but is ISA the right place for this?
Yeah, so there was some work that someone was doing at the University of Michigan like last year. I don't know how it ended up turning out, but they I should probably bump them on getting results about that. But they were doing like LLVM-IR and then doing the modeling on the IR rather than at the ISA level. So yeah, it's definitely, doing it at that level should theoretically be doable. It's just it would require a couple modifications, but it would definitely be interesting. And fine tuning on, so granted, another thing that they did was multitask learning, where essentially you'd have a single model and then you'd share most of the weights, and then you'd have a couple task specific layers, and then it would predict multiple different architectures. So like that sort of fine tuning is something that's already been experimented with, where you could theoretically, I mean, it was trained in parallel, but you could just provide a base model and then train on top of that.
Let's thank Aiden again.